It's a great pleasure to welcome Tom Trogdon to give the Applied Mathematics seminar today. Tom has, well, he's one of the foremost experts in random matrix theory and in particular in seeing fine random matrix asymptotics in the real world. And here it's a sort of different point of view. I think it's about random matrices and the interactions with numerical linear algebra. And he's combining lots of classic random matrix techniques. I'm very excited personally to hear this. So yeah, so this is about perturbations of orthogonal polynomials, Riemann Hilbert problems, random matrices, and numerical linear algebra. Please, Tom.
All right. Thank you, Elliot. Thanks for the kind introduction, and it's very nice to be with all of you today. So please, at any point, interrupt me. I'm going to try to touch on a lot of different things, and if something's unclear, just shout out. Right. So as Elliot mentioned, I'm going to talk about really a problem that's at the core of orthogonal polynomials, or really understanding perturbations of orthogonal polynomials. That's kind of a complicated, nuanced problem. And I'm going to try to tease out some aspects of that and then use it to understand algorithms from numerical linear algebra, and specifically what they do to random matrices. Okay, so different parts of this are joint work with Percy Deift, Xuicai and Elliot. And this is roughly what I'll talk about. So I'll kind of go back through the theory of orthogonal polynomials, discuss some mappings that are very important to the whole theory. And then I'll kind of take a detour into complex function theory and talk about Riemann Hilbert problems briefly, and kind of just hopefully motivate how you can use those to understand perturbations of orthogonal polynomials. These Riemann Hilbert problems have been used for decades now to understand the asymptotics of orthogonal polynomials, but this is kind of a slightly different twist on that picture. And then lastly, I'll try to apply everything to understand what happens when you apply numerical algorithms to large random matrices. And okay, so let me just give this slide here. And I think a lot of the stuff on the slide is not properly defined at this point. The slide will come back up later on. So kind of wanted to show it twice just to kind of give you an idea. And so a lot of this work came out of work I did during my postdoc with Percy Deift, where we kind of just asked, it was almost I don't know, it was maybe an obvious question, maybe not so obvious depending on your perspective, but we said a lot is known about random matrix distributions. And then there's some algorithms out there. There's like the QR eigenvalue algorithm. There's something called the TOTA algorithm that are highly structured dynamical systems. And I mean, they also work as algorithms, but they're very, very structured. And we said something interesting has to happen when you stick these two things together. It was more of a kind of a motivated by mathematical physics perspective, but since then we've kind of pushed it more towards what's actually happening in numerical linear algebra. And so in this slide, we have what I'm going to do is run the conjugate gradient algorithm to solve a linear system, Wx. So we have W is our coefficient matrix, B is our right-hand side. And I'm going to record how many iterations of this iterative method do I need to achieve some tolerance. And I'll make all these kind of quantities precise later on. But what we noticed is, right, if we take a 20 by 20 matrix, we run the conjugate gradient algorithm on it, and this is representing a histogram of the iteration counts, the number of steps you need to solve the problem to a specified tolerance epsilon. Okay, and this dot here is going to be suggestive of something that we'll see come out, right? And so what we noticed is concentrating on this histogram, as the matrix size increased within this Wishart class of matrices, Wishart distribution, what we notice is as the matrix size increases, this histogram begins to concentrate. So the number of iterations that you realize starts to decrease. This is all with 20,000 samples until you get to a really large matrix and you run 20,000 trials. And every single time you take 22 steps to achieve your tolerance, right? So you have a bona fide random matrix, but somehow the algorithm is behaving in a somewhat deterministic way. And so we really just set out, okay, how can we understand exactly what's happening here and how pervasive is this kind of phenomenon? And so by the end, I'll kind of explain exactly why this is happening. And so we'll pass through orthogonal polynomials to kind of get there. And for those of you who are somewhat familiar with conjugate gradient, is kind of a preview, is it's intimately tied with the Lanczos tridiagonalization algorithm, and Lanczos is intimately tied with orthogonal polynomials. So that's kind of how we're going to get there. Okay, so let's kind of take a step back and now consider kind of the classical setup of orthogonal polynomials. So we start with some measure mu defined on the real line, and we first look for the monic orthogonal polynomials. These are the polynomials with leading coefficient 1, and then they have, I guess this should be a constant here. They're not normalized, they're not orthonormal. So there's going to be some constant Cn sitting right there. Okay, so they're orthogonal, they have leading coefficient 1. There's some other quantities that are important. So these are the orthonormal polynomials, the normalized ones. And then this here is what we'll call Cauchy transform of the monic polynomials. So these are all kind of quantities that will come into play. I would argue one of the most important aspects of orthogonal polynomials is the fact that they satisfy a three-term recurrence relation. This is when you're working with, say, Chebyshev polynomials in a computational context, this is extremely useful. Basically, what it tells you is if you take your polynomial, you multiply it by x, it tells you how to re-expand that in the basis, and it's very simple. And another way to visualize the three-term recurrence relationship is if you take a vector of all your polynomials and you do the operator that is multiplication by x, it tells you that is tridiagonal. Right, so symmetric and tridiagonal. And so we will take these three-term recurrence coefficients and we'll put them in this matrix, and that will be called the Jacobi operator associated to mu. Right, so one way to think about that is you have your measure mu, you do Graham-Schmidt on it to build your monic orthogonal polynomials, and then you collect your recurrence coefficients and you can build the Jacobi matrix. So there's kind of a nice well-defined mapping from measure to this Jacobi matrix or operator, whatever you want to call it. And so there's another quantity which is also really comes up in random matrix theory quite a bit, but also is important here, is the Stieltjes transform of the measure. So we have the orthogonality measure here, and this is up to a constant multiple, just the Cauchy transform. Okay, so we're take our measure mu, and then this gives us an analytic function in the complex plane away from the support of the measure. Okay, and so then there's another quantity that you can then connect to the Stieltjes transform just by, expanding the 1 over x minus z in a series at infinity, and you get some sort of asymptotic series that involves the moments. Right, so now this connects the moments of the measure to the Stieltjes transform. And okay, so this is kind of really where I wanted to get with all these things. So we have the measure that we're considering the polynomials orthogonal to. We have the monic polynomials. We have the normalized ones. We have these, which are the Cauchy integrals of these. We have the Jacobi matrix. We have the moments, and we have the Stieltjes transform. So there's kind of all of these, I like to think of them as different quantities that are orbiting the central measure that you're considering. And just want to spend a little bit of time talking about how you get between these things. right? So this one is obvious. I guess you do need information about mu to do this step, but you just normalize to get from the monic to the orthonormal. Maybe what's less clear at this point is you can actually go directly from the monic polynomials to the Jacobi matrix, to the A's and the B's in that tridiagonal matrix by analyzing the asymptotics of these polynomials. Okay, that one was clear. You just take the Cauchy transform to get to the C's. Okay, one way to construct the monics is just to use Gram-Schmidt. Okay, and then the moments are connected to the mu, say classical moment problem, hamburger moment problem. And then, okay, the Stieltjes transform is then, of course, connected just to these Cauchy transforms by it's just a constant multiple of the first one. Okay. And then we also showed how you can get from the Stieltjes transform doing a series at infinity to get to the moments, right? And I mean, all of this is just to say that there's all these quantities and they're basically equivalent. Depending, you know, they really all define mu, and mu can be used to then construct it. But what I'm trying to think about is how do I take this measure mu and go to the polynomials? And it's basically, I think, okay, you do Gram-Schmidt, and how does that mapping behave? And this kind of classical work, okay, I should close that, of Gaussian, he talks about these different mappings. I mean, how well conditioned they are. And he's really thinking from a computational perspective. How do you compute these things? How do you compute with them? And what kind of rounding errors are going to creep in, things like that. But we're going to try to do some asymptotics, so the same kind of considerations come into play here. Right, so let's think about how conditioned or ill-conditioned is the mapping from the measure to the orthonormal polynomials. There's a classical construction that you can just basically build the polynomials directly using Hankel determinants involving the moments. Okay, so this is then really saying, okay, I'm going to go from the measure mu, I'm going to compute its moments, and then I'm going to use its moments to construct my orthonormal. So how does that behave? And so what I did here is, just as an example, this is the degree 4 polynomial. Is I took, this is, so we just have the Chebyshev second kind polynomials. And I took the moments and I took the fourth moment and I perturbed it very slightly. And I looked at what do you get. So the blue curve is the true one and the yellow curve is perturbing that moment by just a tiny bit. Right? And so it's kind of like this small perturbation of the moment changes the polynomial significance. Right? So it's not that surprising. You're doing moments and you have a determinant and that this thing is going to be somehow exponentially unstable. And it is. Right? Small changes in the moments will give you huge changes in the polynomials. Okay, so let's go back to this picture. And really what let's see here. Okay, so we've talked about that. Let's fill in a couple other errors. There's kind of a well-known recovery formula. This depends somewhat on the regularity of mu, but you can look at the Stieltjes transform in the complex plane as it approaches the support of the measure, and you can recover mu using some sort of a nice limit. This is also an important thing. So it turns out that the Jacobi matrix is directly related to the Stieltjes transform through this formula. You basically take the resolvent and take the 1-1 entry. And so the 1-1 entry of the resolvent of the Jacobi matrix is the Stieltjes transform of the measure. So this is somewhat non-trivial here, but it's a nice connection between all these things. And so in a sense that will come up later on. Okay, but really what I'm considering and I'm concerned about is how do I understand the mapping from mu to this Jacobi matrix? And I claim this is directly related to the tridiagonalization of a matrix using, say, Lanczos or Householder reflector, something like that. Okay, and this is, I don't actually really know how to do this. I don't know what metric I would put on mu to understand how perturbations, it's not exactly clear what you want to do there. But what we're going to do instead is start with measure mu, go to the Stieltjes transform, and then use the Stieltjes transform to go back to the Jacobi matrix. And this is kind of gives us a roundabout, a way of avoiding this kind of, in some sense, ill-conditioned mapping. It's still ill-conditioned, but it will be able to determine conditions so it's not so complicated. Okay. So let's connect it back to numerical linear algebra. So here, okay, if you're familiar with it, then this is kind of, yes, this is Lanczos. If you're not familiar with it, the thing to take away is it's a very straightforward, simple algorithm. What it does is effectively it does a lot more than this, but it tridiagonalizes a matrix using a unitary similarity transformation. Right, so the Lanczos iteration acts on this, basically this Krylov subspace, and it builds, I claim that it builds basically the Jacobi operator. So let's see here. So what we're going to do, let me take a step back, is we're going to take a matrix W and a right-hand side vector B. I'm going to compute the eigenvalues of W, and then I'm going to compute these weights, which are really the projection of B onto the eigenbasis. So I'm going to consider this weighted discrete measure. And then I'm going to do Gram-Schmidt on this thing with the monomials, using this as my inner product, as my measure for orthogonality. And I'm going to get the monic orthogonal polynomials. From those, I'm going to pull out the Jacobi matrix. Okay. And it turns out that the Jacobi matrix you get from that is exactly the same thing you would get from running the Lanczos procedure. These A's and the B's that come in up here are exactly the same thing. Right? So there's kind of, this is really the tight connection between the Lanczos iteration and orthogonal polynomials. Okay. So now I'm going to kind of put that aside. We'll come back to it, but I want to talk about how an approach to understand the perturbation theory for orthogonal polynomials. Okay, and so this all goes through this kind of somewhat famous Fokas-Its-Kitaev Riemann Hilbert problem. I guess in the Bright community, it's extremely famous. And what is it? So I guess I also need to kind of say what a Riemann Hilbert problem is. So a Riemann Hilbert problem is a boundary value problem in the complex plane. So you have different regions of the complex plane, you have an analytic function in each region, and as you transition from one region to another, you have some sort of a jump condition that gives you how that discontinuity is defined. Right, so in this case, it's just going to basically be the real axis. You have an analytic function in the upper half plane, an analytic function in the lower half plane, which is this function as a function of z. It's analytic. And then when you go to the real axis from above, compare it to what you get from the real axis from below, you get this triangular jump that involves the density per row. Right? And so this is kind of now a complex analytic problem for the orthogonal polynomials. So if I can find some sort of new method to compute what this yn is, it's going to give me information about the pi n and the cn and so on. Okay. And basically, because you're dealing with polynomials, you know that this thing grows as z to the n at infinity. So it has some sort of a normalization condition. That's really where the degree n comes in. It comes only in the normalization. So this involves the density, right? It basically is one way to understand how you go from the density to the polynomials. It's really Gram-Schmidt under the hood, but it's passing through this somewhat complicated complex analysis machinery in a sense. But what I claim is that you can transform this Riemann Hilbert problem to something that exists off the support of the measure. And you do this using this Cauchy transform, this C0 function, really the Stieltjes transform up to the constant multiple. And so I just take my support of my measure, I draw some curve around it, and I do a redefinition here, actually, inside. So this is a redefinition inside. And it turns out that this knocks out everything that's happening inside, creates a function that's analytic inside, analytic outside, and then you end up with a new Riemann Hilbert problem, a new jump condition on this curved gamma. So somehow you've taken your measure that sits maybe on some sort of finite intervals on the real axis, and you've pulled it off to a jump condition that exists around it. Okay, so now we're getting to the place where we can actually connect two measures to each other. So this C here, it plays an important role, but for the most part, you can ignore its how it comes in. Let's for the most part in this talk, just think of C being one. It's a technical thing. So, okay, I'm going to define basically the ratio of these solutions of the Riemann Hilbert. So this, you can show that this matrix actually has unit determinant. So I have a nice, well-defined, easy to compute inverse. And so I take, let's say I know something about mu. So I know something about this matrix. And I want to deduce something about another measure nu, or the orthogonal polynomials with respect to another measure nu. So I look at this quantity, and again, this is how this whole business works. This solves now another Riemann problem. We're basically taking the ratio of two solutions of a Riemann Hilbert problem. If they're very close to each other, the jump condition, the discontinuity these things should have, should be very small. And so then you end up, you just calculate and you see that this is now an analytic function outside sigma or outside gamma, inside gamma, and has a new jump condition here. And okay, because these both have the same normalization at infinity, we get nice identity asymptotics for the large Z behavior. And what does the jump condition look like? Well, the jump condition has this piece, right, sitting right here. So this is, since the Stieltjes transform is linear, this is just the difference of the Stieltjes transforms or the Cauchy integrals of the measure mu and the measure nu. Okay, there's also this kind of complicating factor here, which I'll talk about. But if mu is very close to nu, this is going to be very small. We're going to have a jump that's nearly the identity. And you can actually recast this whole thing as a singular near identity singular integral equation, and you can compute an asymptotic expansion that way. Right, so I guess the idea is if mu is close to nu, we end up with a near identity Riemann Hilbert problem, and that's something we can handle. Okay, and so this is a little bit of a complicated statement. It's here for completeness, but this is really the thing that I just want to. I'm supposing, say I know a lot about the orthogonal polynomials with respect to some measure mu. I want to know something about the orthogonals with polynomials with respect to some measure nu. I can connect them through this matrix X. And X has at least, okay, a first order expansion of this form, which involves an integral of the difference of the Stieltjes transforms. Right, so if mu is very close to nu, this thing is close to the identity, which kind of confirms that, okay, these orthogonal polynomials should be close to those. Okay, there's a host of technical challenges that come into this approach. Right, so this matrix here, this involves the polynomials, orthogonal polynomials with respect to mu. This thing will typically grow exponentially in the complex plane as the degree increases. So that's a problem. So, okay, that might make you say that, okay, then let's actually shrink everything down towards the support where things are well controlled, but then this thing is never going to be a good approximation if you go too close. Right? Any deviation is going to be picked up for Z sufficiently close. Okay, a little bit of a typo, but the first two. So basically, you need to shrink in towards the support. You need to look at values of Z that are near the support, but they can't be too close. And so there's kind of a balancing act that you have to play with. Balancing this growth or canceling away this growth while not getting too close. This kind of gives us a sense of what does it mean for one sequence of orthogonal polynomials to be close to another sequence. So what does it mean for, that to be true, right? So the first thing you might say is, okay, it should satisfy something like this. I don't even know exactly what I want to mean by this, but okay, that's certainly not a good thing, because this would say that the zeros of these two things coincide, right? And this would actually not give you, this would say that they have to be exactly the same polynomial. Another thing you could say is, okay, maybe it looks something like this. So instead of relative, we have some sort of absolute. And while this is all fine, it doesn't give you enough dependence on z, right? What is the real dependence of z on the error term? That's going to be very important for what we're considering. And so basically, this approach tells you that the expansion should be something of this form. You just go back and you work out. So we had yn for nu is equal to some matrix times yn for mu. And you just work out what that means. And it basically says that you should have something of this form where we have small f1 and f2, right? And you should, to get the next order expansion, you should actually have a lower degree polynomial involved. And so this is really how to compare two families of polynomials. And this, having this one involved allows you to change the zeros of this one in a non-trivial way, because they have to change. Okay, so how is this applied? So let's think about a scenario. We have a large n by n symmetric matrix, and we have some sort of right-hand side vector we're thinking that is also an Rn. We construct this so-called like empirical measure that has deltas at the eigenvalues of W, and then the weights are determined by the eigenprojections. And let's hypothesize that we have, okay, this is potentially some sort of complicated measure supported on multiple intervals, right? So you have maybe a couple intervals and then some delta masses maybe we want to put in there for good measure. And so let's suppose that this quantity, the difference of the Stieltjes transforms, satisfies this order relation. So that it is 1 over square root of n, so the matrix size times eta, where eta is the distance to the support of the measure. So this quantity has to kind of blow up as you get towards the support. Okay. Right, so we have a large matrix. We take its discrete measure computed using the eigenvalues and projections on using eigenvalues and eigenprojections, and we're hypothesizing that it is close to some limiting continuous object. Okay, so, right. To apply this theory, you need this thing to be close to the identity. Okay, and so what does that mean? So, okay, this is an extremely non-trivial bound to obtain. This is actually obtained using the asymptotics for the polynomials with respect to mu, which now that you're on multiple intervals, it involves theta functions and Riemann surfaces, and it's kind of it's a well-trodden path, but it's a complicated calculation to go through. Okay, but you can get a bound of this form. Okay, and then we say, okay, so if we want this thing to be reasonable, we need to get rid of the exponential behavior, right? Which tells us immediately that n has to shrink sufficiently fast. So now, or I should, eta has to shrink sufficiently fast with respect to n, that's what I should say. Okay. So now we're in this situation where I've plugged in the bound for C0. So this is order 1 over, this is what we're guessing. Okay, so I basically plug that in here. And so we have a relationship with n, and so we finally get this kind of a bound here, which actually tells us that now this little n has to be less than, asymptotically less than n to the 1/6. Okay, so this is what we get out. This is far from optimal, certainly, but this allows us to actually let the degree of the polynomial increase with the matrix size in this sense. So you can do an unbounded number of iterations of your algorithm and still analyze it. That's kind of the takeaway. Okay. Right. I should tell you these formulas don't matter so much for this talk, but this is how you recover the coefficients, the entries in the Jacobi matrix from the asymptotics of the polynomials themselves. But basically, this is really kind of the conclusion from the model scenario. If all those things are satisfied, you have a large matrix, its discrete measure is close to some limiting object, then the Lanczos iteration applied to that system will produce approximately the Jacobi operator associated with the limiting measure, provided n is much less than n to the 1/6. Yeah, I believe this can be, this is not optimal, but that's certainly true. Okay, and so now, basically, I gave you the model scenario. There's nothing random about it. What's going to turn out is that random matrices they fit perfectly into that model scenario. But let's kind of go back and start with an explicit calculation that is really, I think it's enlightening. Okay, so let's start with the building blocks of, I guess this would be Gaussian random matrix theory. We have, and maybe before I go into this, does anybody have questions about the previous orthogonal polynomial, the Riemann Hilbert world?
Yeah, so when the little n is less than capital N to the 1/6, I guess you're showing it here. The actual statistics, not the statistic, but the actual the thing you're computing here is you're comparing the Jacobi matrices, right?
Right.
But I guess in principle, okay, you also compare in some sense point-wise the polynomials.
Yes.
I see. And
yeah.
Presumably the moments. I mean, maybe that's not the goal, but anything that you can extract from this type of representation. Okay.
Yeah. So pretty much, yeah. Anything. Okay. This doesn't, because we're kind of moved everything away from the support. You can't. I guess you can undo that transformation and go down to the support. But basically, it immediately gives you anything that involves point-wise calculations of the polynomials, and even. And this comes from the Riemann Hilbert theory. There is, you get this here. So you can look at large z behavior. So limits at as z goes to infinity are also part of the game too.
And the goal is always to get vanishing corrections or vanishing errors between, for example, the Jacobi matrices.
Yeah, that's right.
Okay.
And I should say, I mean, there's been other studies for perturbations of orthogonal polynomials, and I mean, if somebody else knows of some that is kind of this flavor, please let me know. But usually in my experience, people consider, so I take this measure and I do an explicit transformation of it, some sort of rational transformation, and now I want to compute the new Jacobi matrix associated with that one explicitly and find like that mapping, rather than doing kind of an infinitesimal perturbation theory of the measure.
Can you get like a first order correction also?
Yeah, so that's basically this. Right, and so we would, basically assuming, so this is some sort of limiting measure, we know this quantity well, and so then all of the correction comes in here.
And did it matter at any point that one of the measures was atomic, or?
No, and that's kind of the point, right? Because if you try to go and compare these things in some reasonable way on the support, and one is all just Dirac's, how it becomes more difficult to try to do this. But once you stick in the world of the Stieltjes transform around it, you kind of avoid all of those technical considerations, provided you have this very strong condition that, let's see, this very strong condition here. Yes, Simone.
Yeah, I also had a question. So you already commented on that, the sharpness of the error bound, I guess, involving capital N and a lowercase n. I was wondering if you had any numerical kind of evidence that points towards what was the optimal rate to expect.
Yeah, so I mean, given this assumption, I don't know what the optimal rate is, but I can say that in the random matrix setting we go to, this is what we use. This is a consequence of that theory, but I do believe that in the end, all you need is, you can just take this exponent out. It should be n less than n. I believe in the random matrix setting, that's, I mean, at least numerically, it's pretty obvious that that's the case. But yeah, so all previous work has basically been fixed n, fixed little n and send capital N to infinity. And so now this lets us go at some small, I guess, polynomial rate, and then really to find the optimal, it's, yeah, that's, I believe it's, at least in the Gaussian case, we know that that's it, the case. I'm going to show you the construction that will get you there.
Thank you.
So on that note, let's go to that construction. Right, so building blocks of, I guess, Gaussian random matrix theory. So you have this Geneva ensemble, which is an n by m matrix. I'm always going to divide by square root of m to keep everything normalized as I want. And then the complex one is basically constructed using independent copies. Okay, then this is, we're not going to really use the Gaussian unitary ensemble, but just, you know, this is how you would construct it. You would take two complex Geneva matrices, and then you would add, or you take one complex Geneva matrix and you'd add it to its Hermitian conjugate. And so maybe the first appearance of random matrices is in the work of John Wishart, where this X would be a real Geneva matrix. And so this is kind of the, you know, widely studied case of a sample covariance matrix with trivial covariance. Right, and so that's saying this, you take a real Geneva matrix, you have XX transpose, or you could do the complex case, you could take a complex Geneva matrix. Right, and of course, there's no reason why the X need to be Gauss, or the entries need to be Gaussian. Say a little bit about that. There's also no reason why the entries in each column need to be independent. You could have some sort of non-trivial covariance. Okay, but for this calculation that I'm going to do, is everything's going to be Gaussian. Okay, and so the well-known limiting distribution for this matrix, provided m goes to infinity proportional to d, or proportional to n, is the Marchenko-Pastor distribution given here. Okay, so we have a nice limiting distribution for the eigenvalues. And I put this up just because all of this stuff has been tied to numerical linear algebra, arguably since close to the beginning. So this is work of von Neumann and Goldstein, where they, you know, tried to understand condition numbers of random matrices just as a proxy for understanding what's the difficulty of a typical linear algebra problem. And you know, that actually preceded the work of Wigner that gave rise to kind of Wigner matrices, what we think about today of random symmetric or random Hermitian matrices. Okay, this is kind of just to give you an idea that I believe random matrix theory and numerical analysis are really tied from the beginning. There's a lot of works that couple all these ideas, sampling from random matrix distributions. But really here, I'm going to be thinking about analyzing random matrices, algorithms applied to random matrices. Okay, and this is kind of more related to stuff I'll talk later on with this concentration of this, the halting time. You know, it's kind of been analyzed in various contexts in these two papers. And it kind of goes beyond. Pennington and Wara have this nice kind of free probability. They use it to analyze different deep learning ideas. So I think it goes throughout a lot of different current topics. Okay, but back to the Gaussian setting. I'm going to take my Wishart matrix and I want to put it into tridiagonal form, right? And so if you're going to do this, the kind of classical and probably arguably the most stable way to do this is to use householder reflectors. And let me just show you, for the sake of time, how this all works. So I scale it this way. So all of these crosses you can think of as independent standard normal random variables. And what I'm going to first do is multiply on the left by a householder reflector that's going to zero out this row. Right? And so, okay, it's zero out this row, but it's a unitary matrix. So this, what's here has to be the norm of the entries in the row, which means if this is an n by m matrix, this is a chi-m random variable. Okay, but there's a nice invariance that happens. So this one only depends on this row, independent of all the other rows. This distribution is invariant under unitary transformations, so its distribution does not change. Okay, and so then what I do is I apply a matrix on the left to now zero out everything below this entry, below the 1, 1 entry, or I guess I should say the 2, 1 entry in this first column. Okay, and then I guess in this cartoon we had 5 entries, so we end up with a chi-5 random variable. And so now my next task is going to be to zero out as many entries as I can here. So I multiply on the right by another householder reflector, and I get a chi-m minus 1. And at these points, these are all independent as you trace everything through this process. Okay, and now I'm going to work with this. Now I'm going to work with this. Right, so this is just the goal of Gahan bidiagonalization of a rectangular matrix. So now we'll use that, get chi-1. Last step is going to be zero out that. Okay, this matrix of all zeros. Right, so you can bidiagonalize, and this is well known, going back to, I think Silverstein, Jack Silverstein is he goes back to at least him. So you can actually calculate the full distribution of the matrix after tridiagonalization. And all of these entries are independent. Okay. And so what that actually tells us is that if we take our Wishart matrix, we tridiagonalize it using householder reflectors, we're going to get HH transpose where H is this matrix. And so this is going to be our so this is HH transpose is then tridiagonal, symmetric tridiagonal. Okay, now let's think about what happens as the matrix size goes to infinity here. Right, so we have this matrix. If M goes to infinity with D, it turns out that this will converge to square root of D. This ratio will converge to 1. And basically this random tridiagonal matrix becomes deterministic effectively in the limit. Right, and so you get this symmetric tridiagonal matrix, and you ask, okay, what is this? Well, it's nothing other than the Jacobi matrix for the Marchenko-Pastur law. And it actually has to be because of all these connections between Lanczos and orthogonal polynomials and so on. Okay, so, and you can actually compute with this, and you can see that, okay, this, in this case, if n, let's see, if n is less than n, you do get the leading order limit that you would expect. It does become deterministic, provided this is true. Okay, so you can kind of compute everything in the Gaussian case. You know, you have full distributions, you can see what everything's going on there. But what happens in the general case when you have non-Gaussian entries, you might have non-trivial covariance, your matrix might even have some spikes, might have some discrete eigenvalues that persist outside the bulk. And that's where these anisotropic local laws come into play. They basically just say, okay, here's the resolvent of our random matrix. Let's compare it to the Stieltjes transform of the limiting measure. And you get estimates, and this is the kind of piece that we want. This 1 over square root of n times theta, which is exactly what I put up before in the model scenario, right? And importantly, so this is for any vectors u and v, or v and w. If you choose them both to be b, you actually get exactly the Stieltjes transform of this discrete measure that you're looking to analyze, right? So with judicious choice of v and w, I get exactly the C0 of mu minus nu. I guess that is z here. And I get exactly a probabilistic estimate on that one. So what does this tell us then? It says, okay, suppose we have a local law. Then the first n iterations of Lanczos will approximately produce the upper left corner of the deterministic Jacobi matrix associated to mu, okay, with this technical condition on it. Okay, and then there's going to be some fluctuations around that and contained in the errors, right? And so this is the kind of thing that I think Elliot was asking about, is you can get also, say, pointwise behavior of the associated orthogonal polynomials, and actually compare them as a function of z in the complex. And right, so this tells us that the tridiagonalization of a random matrix becomes deterministic and is determined by the 3-term recurrence of the limiting law for the eigenvalues of the matrix, which is kind of known, but what's kind of the improvement, the main improvement here is that you can take more and more iterations as the matrix size increases. Okay, so now let me try to return in the last few minutes to my previous, my motivating slide. Don't have a lot of time, so right, here's the conjugate gradient algorithm. Yes, and then this is my stopping criteria. I'm going to run it until my residual vector, which is defined as this, where this is my approximate solution, until this is in norm less than epsilon. And so this, when w and b are random, this is a random variable, right? And then this is the picture we saw before. And this is basically because the tridiagonal matrix from Lanczos is becoming deterministic. Bit behind, so you can, these two theorems that Elliot and I established basically show you what you can do in the Gaussian case and give explicit distributions there. And so you can kind of push the computation till the end very easily in the Gaussian case. But what happens for the non-Gaussian case? I just want to, maybe I'll just say this. So it turns out that the residual at step k in the iteration of conjugate gradient can be obtained using this formula for the orthogonal polynomials. Right, so if you want to see how well did conjugate gradient do, you compute the orthogonal polynomials, you evaluate this quantity, and it tells you it's an exact formula for the residual that you get at step k. So now that we can analyze asymptotics of polynomials in the complex plane, even large z limits thereof, we can analyze this formula and get, a paraphrased conclusion that once you have a local law, the residual at step k for conjugate gradient will concentrate on a deterministic value. Right, so this is this precisely, actually I'm going backwards. This is precisely this phenomenon, right, where the algorithm starts to become deterministic. And let me just finish showing a few plots. This takes a little bit to kind of parse here, but what this gray region here is just a bunch of samples running conjugate gradient on it, looking at the 2 norm of the residual at each step. Let's ignore this picture for time being. And then this histogram here is really giving the distribution of the iterations to hit this error threshold epsilon. And so the black curve is the theoretical limiting value for the residual. And then as you take the matrix size larger, basically the residuals that you experience concentrate on a known deterministic value, and then the histogram for the halting time, the runtime, starts to concentrate. So that was Wishart. And you can also do this for spike covariance matrices where you have some number of deltas in your limiting measure. And what conjugate gradient does is it kind of deals with those in some sort of transient period, and then it hits an asymptotic rate of convergence, which you can predict. Telling it exactly what it does in the transient period is kind of a difficult problem. But we know eventually it hits this kind of asymptotic rate. And lastly, I think the more interesting case is when you have, say, a limiting measure for your matrix that has multiple bulk components. What you actually get for a limiting curve for the residuals is some sort of periodic, quasi-periodic thing, which is actually determined by the theta functions that you use in the asymptotics. And I guess that's kind of obvious with retrospect, but you actually get kind of quasi-periodic behavior out of the performance of an algorithm applied to a random matrix, which is, I find, kind of an interesting ending point. And I guess with that, yeah, I'll stop there.
Thank you very much. Okay. Well, do we have questions? Start with one also. So on this figure that we're looking at, these oscillations, these persist in the limit. So this is not a transient effect. This is
right.
Finite end effect.
I think this is actually a nicer way to see it. Is as you run, so this is actually looking at the 3-term recurrence coefficients that come out.
Okay.
And so this is the blue and the red curve are the limiting values that we computed. And then the gray region is the samples.
Mm-hmm.
In the end, like with retrospect, you look back and you say, okay, yeah, actually it's been known that the asymptotics of orthogonal polynomials with measures supported on multiple multiple intervals do have quasi-periodic behavior. Yeah. So of course you're going to see it, but you know, it's kind of only realized that after we did the whole calculation.
And it's also observed in a handful of cases that the optimal first order methods for solving problems can have periodic behavior. If you would believe that CG always searches out the best one, then I guess it shows that there are cases where that's the right thing to do.
Mm-hmm. Yeah, and I mean, this is also the residual. If I looked at the W norm of the error or whatever, the thing that has to be monotonically decreasing, we would have different behavior.
Okay. We have other questions. I can try out
more of a curiosity on the orthogonal polynomial part of your presentation. So I was wondering if same theory can be also kind of tackled in the multi-dimensional case where you have orthogonal polynomials and multivariate polynomials, and then maybe then truncating it's trickier, right? You can have total degree expansion, tensor product, hyperbolic cross. So I guess might be trickier to study kind of the type of asymptotic limits you were proving.
Yeah, I'm trying to think of. I mean, so people have studied. I believe so. I mean, the first step in that direction would be like orthogonal polynomials in the complex plane, not just on the real axis. And then there is, I believe that involved, I could be wrong, involves what's called a D-bar problem, which is now kind of an extra layer of complication. And then if you go to I mean, sure, there's some sort of an extension, but often these things kind of rely on treating one variable and then treating the other. But yeah, certainly worth thinking about.
So you showed a Gaussian process limit for differences of pi at some point.
Yeah, I knew you'd ask about
that. Yeah, like this one. So as you go, as the recurrence evolves longer, I mean, I guess in various situations we know. So for example, if you stay in the plane to some amount, that the fluctuations of pi are exponentiated, that it's the logarithm of pi, which is the Gaussian process approximation. Does anything in your setup let you say things about the logarithm of pi, or?
Yeah, so right, so that's exactly, yeah, that's really important. So there's kind of there's an exponential term, and so if you look at the asymptotics of pi and mu, there's an exponential term, and then kind of the order 1 stuff, or maybe polynomially large stuff. And it turns out when you do this, how you back everything out, that exponential factor ends up in terms of both, in front of both expansions. So you actually can factor out the exponential thing and compare everything on roughly an order 1 scale, which is critical to all of this. I mean, because it's kind of, it's inherent in, right? So you write this formula decays exponentially, right? And so if you want n to increase, and say I have some sort of correction onto this, like when is it actually a correction if the first term is exponentially small, right? That's the main term. But it turns out that you can factor out the exponential decrease in front of everything, and you get an roughly order 1 quantity afterwards.
Is this based off of the representation of in terms of pi n minus 1, pi n minus 1, that one?
Yeah, so maybe I can go back to that. And so basically what you end up with when you do yeah, I guess this is it. So you have these things become random. Those are the things that you're actually analyzing, that they're small random quantities. And that's very important to be able to analyze it that way, as opposed to having something like this plus a random quantity, where now this is, say, completely on a different scale.
Well, do we have any further questions? Maybe we can thank Tom and